Hello and welcome. This is the investigation of the mechanical and degradation properties of 3D printed PLA scaffold designs with Aisling Guteridge, James Frizzell, Jeffrey Ekwem, Michael Grealis and Peter Fagan. In this study, synthetic polymer PLA scaffolds were created. The purpose of a scaffold is to aid in the regeneration of diseased or injured tissue to restore architectural and functional features of the tissue. PLA is often used in biomedical applications as it can be easily modified to enhance the mechanical properties of the polymer. PLA can be mixed with other polymers such as PCl to enhance mechanical properties. Effective scaffolds may provide a supportive, biocompatible frame for cell migration while degrading to allow the tissue to develop without obstruction. The main objectives of this study are to design and create a log pile PLA and solid PLA scaffold using fused deposition modeling, to test the mechanical properties of the scaffolds to determine their compressive moduli, then to analyze results of a 7-day accelerated degradation process carried out on the PLA scaffold designs. For certain applications, porous log pile scaffolds are superior than other scaffold solutions, as they have the ability to maintain high cellular viability throughout the structure. They allow for good cell adhesion and can replicate the environment that it will be applied to due to the accuracy of the manufacturing method used. The manufacturing technique of fused deposition modeling is used due to the compatibility it has with PLA polymer. This results in a simple, cost-effective method which can produce complex but accurate scaffold geometry. The log scaffolds are designed using Fusion 360 software. The thermoplastic material is extruded using a layer-by-layer method. Uniaxial compression testing is carried out on a log pile PLA scaffold and a control solid PLA scaffold using the Zwick biaxial tester. In the degradation study, the scaffolds were placed under the influence of accelerated aging conditions. The scaffolds were incubated in 20 milliliters of sodium hydroxide, which has a pH of 12 at 45 degrees for a week. The sodium hydroxide was changed every 24 hours and the pH was noted after every change. At the end of the week, the scaffolds were removed from the sodium hydroxide and dried to remove any residual liquid. The weight of the scaffolds were recorded. Pre- and post-degradation weights of the scaffolds were recorded. Figure 2 shows the results of the PLA log pile scaffold and solid scaffold. Figure 3 shows that the compressive modulus of this solid scaffold is higher than that of the log pile scaffold. Figure 4 shows that there was a greater loss in mass in the log pile scaffold after both 3 and 7 days in comparison to the solid scaffold. The effects of sodium hydroxide bath is shown. Figure 6 shows an increase in pore size after the 7-day degradation, while there's a decrease in strut size. Similar studies on this topic show the importance of strut and pore size, with optimal physical properties set for pore size to be between 0.16 and 0.7 millimeters. Our results show a Young's modulus for the log pile scaffold to be approximately equal to 75 megapascals, which is promising as the recorded compressive modulus for trabecular bone was found to range from 50 to 100 megapascals. Various factors affect the mechanical properties of PLA scaffolds, such as strut size. It was found that an increased strut size resulted in an increased compressive modulus. Therefore, there is a balance that must be struck between pore size for cell proliferation and strut size for enhanced mechanical properties. The degradation rate of PLA scaffold can be altered and controlled by factors such as geometry, size, and implant location, which is important for effective healing. In conclusion, this study successfully illustrates the importance of scaffold design on overall performance. We have found that pore size has a direct correlation to cell proliferation, demonstrated that strut size affects the stiffness of the scaffold, and that it is possible to replicate the compressive modulus of trabecular bone. Adequate control of degradation rates allow for sufficient regeneration of bone. Our group would like to acknowledge the time, effort, and competence of Dr. Manus Biggs and his team involved for their help in the completion of the study during these unprecedented times.